So I'll be talking about a new package by the muon physics object group in CMS that we've developed over the past year or so to compute Tagandprobe efficiencies efficiently with Apache Spark and Parquet. So I'll spend a little bit of time motivating why this was sort of needed for us and talking a little bit about the technique of the Tagandprobe efficiency. But then I'll show like a short demo just to highlight sort of how easy and convenient it can be. So the idea is to hopefully inspire other groups, other experimental groups to also do something like that. So let me, so why efficiencies, right? So I think if you're in an experimental physics program, it's very likely that you, at some point in the analysis, you're gonna have to derive some efficiency. So whether it's like an object reconstruction efficiency or trigger efficiency, there are several different kinds of efficiencies that we need to compute as experimentalists. And at the same time, many aspects of the physics analysis that we do rely a lot on simulations, on Monte Carlo simulations. So it is really crucial to understand the limitations of our simulations and how and assess the validity of the simulations, because it's impossible to have your simulation to capture every single detector detail. That's just physically impossible. And there's always other physics activity that degrades the performance that you're not aware of beforehand. And so it's really important to measure the discrepancy between the efficiency that you measure in data and the efficiency that you simulate from your Monte Carlo simulation to obtain the correct representation of whatever physics you are studying. And so the way we do that a lot is by deriving the scale factors, which are essentially calibrations between the expected and the observed performance. So that's a really important part of any physics analysis. And so in CMS, in the muon pog, a common way that we compute scale factors is via the Tagandprobe method, which I have a sketch here on the right. But let me just say that in CMS we mainly use the Z or the J psi resonances decaying to two muons to compute the efficiency in data. So on the right here, you see a candidate event for Z boson decaying to two muons. And I have in blue the tag muon and in red the probe muon or the probe track at this point. The idea of the Tagandprobe is that you can use the dimuon resonance, for example, Z here, to tag the muon with a very robust and very tight selection. And also ensure that the muon, that your sample of events corresponds to a dimuon resonance. And then you minimally select the probe, so you don't apply a lot of selection to your probe. And so your probe becomes your test bed, where you can check whatever selection you want and measure the efficiency in data by using as a leverage the tag muon. So that's the idea of the Tagandprobe. You ensure a robust tag and a robust event selection. You apply minimum pre-selections to your probe, and then you can use that probe to see if your selection passes whatever test you are trying to compute the efficiency for. So you can do that both in data and in simulation, and then you can compare the results. And that's how you can derive the scale factor. So that's one main role of the muon physics object group in CMS, is to provide this official scale factors and the efficiency recommendations for all the CMS analysis. And so it's quite a fastidious work, and it requires a really performant code because we have a lot of efficiencies to measure. So I'll show that in a little bit. But this is just to motivate, right? So oops, I think I went. Okay, so here I have a sketch of what a cut and count Tagandprobe computation consists of. So on the left here, you have your sample with your event content, which you then apply a very loose selection to store some flat ntuples. So this is what we call skimming. The idea of a very loose skimming is that you can reduce the size of your data set, but still make it reusable and flexible enough that you can compute all the efficiency that you want. So once you have this ntuples, then you can apply a pre-selection to your tag, as I mentioned, like making sure that you have a very tight tag selection. Oh, I'm sorry, my mouse is going. So you apply a very tight selection to the tag. You apply a loose selection to your probe just to make sure that you have a Z event. And then you can use your probe and apply some denominator selection to it. And then your test selection, it becomes your numerator. So your task selection may pass, your probe may pass or may fail that task selection. So, and this is what we're measuring. We're asking, has this probe in this event that I know is a muon event, does this probe pass whatever efficiency, whatever selection you want? So what we do then is we bin this passing and failing probes in bins of the muon invariant mass. So here's a muon invariant mass, and you can see the Z peak. It's just a sketch, but you can see the Z peak in both cases. And so what you do is you cut, and then you count the number of probes that there are within this window around the Z peak. And then your efficiency just becomes the number of passing probes over the sum of your pass and fail probes. So that's the simple example with the cut and count. You can also, instead of cut and count, you can fit the spectrum to a signal in the background shape that allows you to separate a little bit better the signal in the background. But I won't talk about that because the demo today is just the simple cut and count. But the idea is that then you can do this procedure, right? You start with your scheme, you apply some selections, and then you measure whether your probe passes the task selection or not. And you do that to both the data, to events in data here in orange, or the simulation of your events in simulation in purple. So you do this, you count the probes that pass and that fail the selection, and you get the efficiency in data, and you get the efficiency in the simulation. You can bin in whatever way you want to bin, and then out comes your two efficiencies, the efficiency in data and Monte Carlo, which you can then divide to get the scale factor. So that's the idea for the Tagandprobe. And again, this is a very general idea that serves many kinds of different purposes: trigger efficiencies, identification efficiencies, whatever you want to do. And just to emphasize this point, why we need such a robust performant code is because there are, in CMS, there are a lot of efficiencies to measure. So you can think of, they're all sort of factorized. And so to do an analysis, you need to measure your trigger efficiency. You need to, if you're using isolation requirements, you need to measure that. If you have, of course, you're going to have some identification criteria, and you need to measure that as well. So all of this creates a lot of possible combinations of efficiencies that you need to measure to keep track of. I won't go through all of those, but just to highlight that this is the official list of supported efficiencies by the muon pod, and so there's more than 20 possible combinations. And then for each of these combinations, of course, you don't want to only measure the scale factor, you also want to measure the uncertainty on that. And for that, a lot of systematic variations are required to, on the number of bins, on the binning width, and so on. And in the end, it turns out that we need about, this is just a rough estimate, but about 10,000 fits to get all of the efficiency. So that's a lot of computation. So that's why we need a really fast software. So over the past year, we have been developing just the package. It's called Spark TNP. And so we've been developed inside the muon pod, but this was originally written by Devin Taylor. And the idea of this package is to leverage the CERN's Apache Spark cluster that's called analytix to distribute this computation. And so we also use the columnar data format, which is Apache Parquet, that interfaces with the Spark cluster very efficiently. So by using these two tools, we managed to reduce the scale factor computation time from days before to minutes to an hour, depending on how busy the cluster is. But this is a really significant improvement for us. And we also made this framework available to CMS analyzers because oftentimes an analysis wants to create a new identification criteria that serves the physics model better. And so they can use the Spark TNP to compute the efficiencies for their own custom selection. And so we also training and continue training. We're doing training workshops for all the users and so on. So that's the idea, is to switch to this framework to compute this scale factors much quicker. So the goal today is to talk about the Spark TNP package and mention and highlight the convenience and the speed of the calculation, and hopefully make the framework or the technique available to the wider HEP community. Because as I said, every experimental program needs to measure efficiency, so this could really be used outside. So here's the code base is now public in our muon pod repository. If you want to check it out, I will highlight sort of the workflow of the software. So here you start with your CMS, full event content. Then you run, as I mentioned, the skimmer, the ntupleizer to get your selection of tags and probes. These are the possible tags and probes that you have. You store those as flat root trees in EOS, and then you move them over to HDFS. HDFS is the Hadoop file system at CERN. So this is what Spark uses. Spark can access the HDFS, but it cannot access the EOS. So we have to transfer it to HDFS. Then we convert the root files to Parquet before plugging it into our actual Spark and TNP calculator. And I'll talk about why we spend time doing this conversion from root to Parquet, but it basically saves us a lot of time. And so once we have the Parquet, this is our input. And here we're doing this aggregator, which is flattening. We're calculating the probes that pass and fail whatever selection you want. And then after that, we can either fit the spectrum, as I mentioned, or do the cut and count. And then after that, we just plot the results and calculate the actual scale factor files and efficiency plots and everything. And we make that available on the web page to the CMS analyzers. That's the overall framework. You can see that we use a Spark cluster to do the aggregation step. For the fitting step, we're still using Condor jobs. One goal of the package in the future is to also use Spark to do the fitting jobs. We think that's possible, but we haven't really tried that yet. But to completely drop the requirement on the Condor. But for now, we use Condor for the fitting jobs. So just to match the software to the physics, right? So again, the aggregator is doing that step where you start with the Parquet and tuples with your possible tag and pro pairs. Then you measure, then you look at which pros pass your selection and which pros fail. That you're flattening, that's an aggregator because you're creating a histogram out of all of the tag and pro pairs. Once you have this reduced information, then you can either fit or do the cut and count to estimate the efficiency. And then the results of that go into the plots that we want. So that's the idea. So as I said, we managed to really speed up taginpro efficiency and scale factor computation. So I won't go into too much detail on the left side, but I just to highlight on the right side, with the previous framework we had, which was a pure root-based and root fit-based taginprobe, it would take about a night to calculate a single ID, a single identification criteria using one LX plus core. And by the end, now we are on this time scale of 1 hour to do all of our IDs, all of 20 plus combinations of efficiencies, and that uses using about 100 Spark cores. And a huge speed up was using the converted Parquet files instead of running Spark on top of root files, which we used with this package called Laravel. So from now, so this is quite a significant speed up. And so we wanted to advertise that because we think it can be useful to others. But the package itself has two user modes, which I call the script versus the notebook. So you can use the Jupyter Notebooks in SWAN, which is the service for web-based analysis offered by CERN, to do exploratory work. And that's what I'm going to show today, actually. But you can also do the official production using a command line interface. And that in this way, you just give it a configuration file that defines everything that you want the software to do, and it will do it, and we'll throw the results into a web page, and that's it. So it's really easy to use, and we've had a lot of success with users trying out the package and running their own custom identification efficiencies. So with that introduction, let's go to the demo. So I'm going to move over to the notebook. The scale of the stock interactivity is going to be in this 2 on the Pivarsky scale. That's what I call in terms of interactivity. So I'm going to, unfortunately, we need CERN, SWAN, and the Spark cluster access for this. So I think it's hard for just everyone to follow along. So I'll be showing you how to do, but please feel free. The code base is there, and you can feel free to play around too. So let's see. So let me just ask, can you see, can somebody tell me if you can read the font size?
It's a bit small, but it's readable.
How about now?
That's fine, yeah.
Okay, awesome. So this is the SWAN interface, and it's just a Jupyter Notebook, but it has a few enhanced features. And the idea is that the SWAN service automatically interfaces with the analytics Spark cluster. So this is the really nice thing about this. So it will create a Spark object for you. You don't have to worry about it. So here's, I just restarted the notebook. There's nothing. So there's no Spark object, but now we're gonna click on the star and we're just gonna connect to the Spark cluster, and we'll do that for you automatically, and it will create a Spark object that then we can use. So it will authenticate me, and so on. It's gonna take a little while. So while it does that, I'm gonna switch here to the config file and just show you an example of a configuration file that we're gonna use. So the config file has all the information that you want the efficiency, the Tagandprobe efficiency to run. So here, for example, I'm defining 3 efficiencies. So these are the numerator and the denominator. So lose ID, medium ID, or tight ID. And then you can do the pre-selection, as I mentioned. You apply a selection to the tag and to the muon pair, and you apply some minimum selection to the probe here. And all of those definitions are here. So everything that you use, you need to define. So medium ID is defined here, for example. And so those are the variables inside the ntuple. So basically, you define everything, you define your selection, you define your efficiency, and then you define the binning that you want. So you can have any kind of binning, PT, absolute value of eta, or the number of primary vertices, whatever. If the variable is inside the ntuple in the scheme, you can use that as a binning. And here, you were just giving it the variable, so when we say PT, we really mean the pro PT inside the ntuple. And then we can also give it a pretty name that will be printed. So that's all that the config needs. I mean, there's also some systematic variations that you can define, but I won't go into that here, just for sake of time. Okay, so going back to the notebook, we're now connected to analytics. You can see the green arrow. So if I run the Spark again, you see that it's in the memory now. So we can just use it. So I'm going to just import a few other libraries to show you. I have this nice trick for long-running computations. It's just a beep, it's just a sine wave, but you can put it at the end of your command, and a long-running computation. So hopefully that was not too loud. I'm sorry if it was, but it will just alert us that the computation is done. So, okay, so now what I'm going to do is I'm going to import the Spark TNP libraries, and I'm going to import the configuration file that I just showed you. And with that, the first thing that we want to do is to load the Spark data frame and then do some pre-processing on it. So this is sort of one of the cores of the computation. So this is what we're going to do with the get data frame. We're basically going to load the Parquet files. Right, here's where we're telling Spark to read the Parquet files that we have. And then we are going to apply the definitions in the config file that I just showed you as additional columns in this data frame. And then once we have all the definitions, we can apply the pre-selection to the tags and to the event. And then we can do some other things like applying some weights and creating the binning structure that we want. And then in the end, you have the data frame bin in whatever binning structure you chose in your config file. So those are the main steps to get started. So I'm going to show you. So I'm going to just run that get data frame. And while I forgot to actually define it. But while it runs, so just to show this, what we're doing here, we're using half of 2018 data. So that's in CMS, that's around 2018D, but that's about 32 inverse femtobarns of data, which is quite a large data set. But in the end, after our skimming and tuples, we have about 7 million total tag-probe pairs. So that's how many entries we're running in our data frame. And you see just how fast it is. let me go. So it's loaded our data frame. So now we have the data frame. And just to show you, this is a Spark data frame, which is similar to a pandas data frame, except that all the computations on the data frame happen on the Spark cluster. So you don't really have access to the data frame. It's just kind of the representation of the data frame, because you need the Spark cluster to run computations on it. But just to show, but it has all the variables in the ntuple were loaded into the data frame. Okay, so the first thing we can do, just really quick, is just to make sure that we have something reasonable. So that our taginpro pair really does represent a Z boson. So here I'm plotting the pair, the dimuon invariant mass of the pair, of the taginpro pair, and hopefully it will look reasonable. But you can see this is running in the cluster. And right now we're connected to 24 cores. That number varies a bit depending on how busy it is. We can also look at the computation. And so the yellow is the number of cores that you have available, and the blue is the number of active tasks. So the goal is to maximize the blue as compared to the yellow, but that's not always possible. But in any case, this allows us to keep track of how our computation is proceeding. And so while it's running, let me just tell you about the next step, which is to get, if you remember the slides, is to actually get the pass and fail probes. So here, the next step is to take the data frame and to calculate how many of the probes pass your numerator selection or not. So first we apply the denominator selection. Here we require all of the data frame probes to pass the denominator. And then we do a group by operation on the data frame to bin and to calculate how many of the probes pass the numerator selection. So this is just, asking the question, how many of the probes that pass the denominator also pass the numerator? And that's going to be eventually our efficiency. Then you can see that we do a cut and count. We're basically just cutting on the mass bins to make sure that it's around the Z peak. And then we're recounting how many of events pass inside the mass window. That's basically it. And then we convert the results to a pandas data frame from a Spark data frame, and then we're done. So I think it's almost over here. Okay, so there we go. So you can see it just ran the computation on the Spark cluster. This just produced a plot of the dimuon invariant mass. This was about 2 minutes for 7 million events if you want. So it's really quite efficient in terms of processing time.
And just to say, there's 5 minutes left, including.
Okay, I'm almost done with the basic example.
Yes.
So now we're going to do the pass and fail, which we're going to calculate the efficiency, the number of probes that pass the tight ID over the number of probes that there are tracker muons. So this is going to give us the efficiency. Here I'm using as being the eta, the pseudo rapidity of the muon, but you can choose whatever binning you want, as I said. And so while it runs that, the last step then is to actually compute and plot the efficiency. So we have the probes that pass the tight ID, and we have the probes that fail the tight ID. And now all we do is take the data frame and group it in terms of the ones that pass and the ones that fail, and then we can just calculate the efficiency as pass over fail plus pass. Those are all the steps that are needed, and then we'll have a plot. So it's taking a little longer than usual. I think it's because the cluster is busy, but it's almost done. So I'll just do that one example and then I'll stop for questions, but you can do whatever binning you want. You can do multi-dimensional binning as well, and you can do it's pretty flexible. So this is the main point of the framework. For this notebook, you can do exploratory work. So we could go here and change the bidding, change the IDs, and we can change whatever we want, and then just reload the configuration and then rerun. And you see, like, we have the plots in a few minutes when the cluster is not so slow. Sorry, it's a bit slow today, but maybe while it's finishing the computation, I can take some questions. Does that sound like?
Yeah, sure. Up to you, of course. There are a few questions on the slide, actually.
Okay. I think I'm seeing here at the.
You have the page, or?
Yeah, I have it open.
Okay.
So could you skip the root to Parquet conversion is running with 100 cores and root files via Laravel an option, while with the runtime speed? So we found that running with root files directly by using Laravel significantly slows down the computation. We're not sure why. I mean, this would we would need to take a deeper look, but it might be because of the caching that's done in Laravel. But we find that because you only need to do this conversion once, we find that it's much more efficient to just do the conversion the first time you produce the data sets, and then you just run on Parquet for all the other efficiencies. So that's usually the way that we, but it is an option. It's just slower. Oh, it's done. Let me just plot this. And there you go. We have the tight efficiency as a function of pseudo rapidity, calculated from scratch in just a couple of minutes. So I usually get this to be 1 minute. So it's like 6 million events or so over 60 seconds. So that's about 60,000 events per second. So it's really quite fast. Just to show you why we developed so much effort into this package. But let me take another question then. Does the taginpro process involve any iteration? Caching intermediate results for iteration was promoted as Spark's distinguishing feature over Hadoop originally. Yeah, so I believe it does do caching. But we haven't gone that far in terms of the optimization. But I think you're right, Jim, that we should be able to cache this. You're right that Spark does do caching. I don't know if you take advantage of it automatically. I don't think so. So I think this might be a good idea for getting even better performance for the intermediate results. Yeah. Okay. How can we access the Jupyter Notebook about Apache Spark and Parquet? So the notebooks are in the code base. Here in this link, in the slide. And if you go to the notebooks folder, you can find it there. So just to take a look. You mentioned Laravel, but are you using Python packages from the HEP ecosystem in your workflows? If not, is that because they simply aren't relevant? So I guess I'm not exactly sure which HEP ecosystem packages you're referring to. Maybe this is something that we can discuss on the Slack, because we do. I mean, yeah, I'm not sure which particular high energy physics packages you discuss. We just use PySpark and Matplotlib for now and NumPy. But this could be interesting if there's some packages that we can take advantage of. Okay, could you please explain the cut part again from cut and count name? I don't understand why we call it cut. Oh, you call it cut because you're cutting around the peak. So you have, here you have the whole, you're binning your pass and fail histograms as a function of muon invariant mass, but you want to make sure that your events correspond to Z bosons. So you want to cut around the Z peak. That's what I mean by cut. So you can see the dashed line and the solid line on top of the dashed line. So out of all of the events here, we only use the ones that are inside this cut window. That's what I mean by cutting. Hope that can we use the Spark for jet efficiency calculation as well? I'm not sure what you mean by that, by Spark for jet efficiency calculation. Oh, sorry. Inside of muon, just jets. Yes, I believe you should be able to. I mean, if you can formulate the problem in a similar way of calculating passing probes and failing probes. then you can definitely do this. We have been studying. Now that we have this powerful framework, we can choose whatever binning we want, right? So we've been studying studying the efficiency of muons in the presence of one or more jets. So that's something that we're starting to look at. So for example, this is what this framework allows us to do. I mean, we could do that before, but the flexibility and the performance of this allows us to just, okay, ask the question, how does this efficiency vary as a function of jet multiplicity? Does it change? And so these are the kinds of questions that you can just, if you have that variable in the ntuple, then you can just go in here and add, n jets, and then bin, 0, 1, 2, for example. You could do that, and then you're done. You can redo the computation. So it's really versatile. And so, but to calculate the efficiency of jets themselves, there's probably a little more tweaking that needs to be done, but I don't see why it shouldn't be possible. Yeah. Sorry, I'm trying not to go over too much. But I hope that I was able to give you at least a sense of how easy and fast it is to compute a Tagandprobe efficiency. Like I won't run the rest of the examples. I was just basically doing other binnings. But in just a few minutes, we're able to start from a Parquet file and then just have the efficiency derived, which you can see here.